So hello everybody. As you can see, I'm going to talk about SRv6 and NSM. Who am I? So I work in a technology strategy team at Bell Canada. I do participate in a bunch of various communities when I have the time, mostly FIDO, NSM, and CNCF. I participate and I co-author some ITF drafts. And I am also leading the hardware and software desegregation and P4 development at Bell. Plus, I'm a father of 3 young kids, so my girlfriend has a tendency to tell me that that's my real job, the rest is just hobbies. But the reason why I talk about this is it gives me a good playing ground and viewpoint of how to do those things compared to trying to avoid being stuck in the Conway's law and being able to see a very obvious point when you try to fix a solution. My agenda for today will be talking about some of the problem statements around what I see, what we have lived through. And afterwards, I'm going to talk about what is SRv6, a bit of theory of the networking side. So I come from the networking, as we talked to remember this morning. I'm going to talk about coins. For those who don't know what it is, I'm going to talk about later on. I'm going to talk about the notion of service programming, what can NSM bring to us, and some few use cases. So the problem statement I can explain is a real deployable network service composition is hard. We haven't really seen big, complex deployment of service chains in the network right now. Across providers, we do basic stuff, but the complexity of it has not really been solved before. We largely still see and rely on ACL-based interface classification, on port-based classification, like the basic principles of plumbing. We do a lot of MacGyver-like networking tricks, .1q VLAN tags, we play with the TOS bits. We do route leaks, we do extranets, we're trying to do a physical port service chain, but we try to do it at L3 VPN layer. Right now, we see a blooming of SD-WAN solution, but if you look at this, if you would have a standardized way of doing service chains, that's completely the opposite. Every SD-WAN overlay platform right now has their own magic secret sauce. We still based our service chains on linear patterns, while flows are not, if you look at network service mesh. We still have not reconciled network versus application awareness. So we're all in the SD-WAN, the DPI, application reality, figure out how our chains work. But in reality, some of us like operators, we still have a basic how to chain an Ethernet port from our carrier network into a DDoS engine to go, which is a basic plumbing. And we have installed the local versus remote or multi-cloud dilemma. By that I mean, if you look at all the UCPE flavors we have in the industry right now, all of this is kind of magic trick per vendor, per OS flavor that runs there. When you do this, how do you reconcile the network in the cloud? It's completely different. And afterwards, if you want to do multi-cloud services, it goes even beyond. So that the full breadth of a service chain that can grow from on-prem in a telco cloud and a multi-cloud has not been solved yet, at least to my knowledge. If somebody has figured it out, I'd like to know. So what I want to see is like this is kind of a service graphs. It came from the initial research from or the work from Paul Quinn on NSH service chaining. And if you look at this, it strangely resembles a service mesh in the application layer of cloud native right now. So when faced with unsurmountable odds, where we are going to have to science the out of this. So to go where I'm going to go into a bit of theory of networking. I know it's going to probably be something new for some people. For others, sorry about that. So I'm going to talk about what is actually segment routing IPv6. We've talked about this before. I've talked about this numerous times on the working group calls on the Tuesdays, but here's what it is. So it's a source routing paradigm like segment routing MPLS. The basic is that you engineer the routing path at the source to be able to encode what you want to do. In the case of segment routing v6, the segments of the traffic flow are represented like an IPv6 address. They are not IPv6 address. They're under 28-bit SIDs. The segment lists are carried into a segment routing extension header with the SRh, which is about this week should be ratified as a full-blown RFC because while we're doing that show, there's a ITF show in Singapore. And this is following the RFC 200 specifications for IPv6. SRh has been built to be able to carry multiple other informations, like in TLVs, to HMAC, NAV metadata, or OAM if needed. And you can leverage the tag field in there to be able to add new kind of poor man's ACLs or simplified tagging. In the case of Kubernetes, really good if you want to do label-based policies without having to do the full-blown ACLs every time at every compute node. And try to remap that into IP tables. So, and the principles of IP segment routing v6 works with every node in the path where there's actually a segment routing endpoint. You swap the address, the destination address of the overlying IPv6 header with the active segment in the segment list. When you get to the bottom of the list, the last segment, which is the final destination address, you can remove everything else and that you go on. Why segment routing is so interesting for a lot of people? Actually, there's about 7 or 8 deployments, mostly in China, but we have Uganda now and some in Europe. Well, it still uses standard IPv6 routing. There's no need for a special IPFib table. The devices can do full-blown IPv6 routing. It's actually ideally suited for microservices at scale. If you think about pods into a Kubernetes environment, if they were in IPv6, there's a bunch of things we do with NAT that can actually be resolved for you to be able to leverage that at full-blown routing scheme. And there's a stateless underlay, which is actually interesting. That means that the boxes in the middle don't have to think about doing anything else but forward IPv6 traffic. Only the endpoints that required SRH to be processed need to support it. The other ones don't have to worry about anything, so you simplify your network capabilities. It's also something which is really interesting for a lot of carriers. If you think about this, it's actually a single encapsulation that can actually do both overlay and underlay forwarding. So you can use it to do basic network transport traffic engineering, but you can also go and play with the application level and play with metadata and service function chaining. Now I do a shameless plug about Crave TV, which is some of our video on-demand service in Canada. Again, also in segment routing v6, because a lot of people have complained about the potential problem with the overhead of the IP of the header. There's actually 3 modes of how it works. So if you only have one segment and you have no need for TLVs and tags, it's just a pure IP and IP encapsulation. If you have a lot of list of segments, or you need the tag fields and the TLVs, you do the full-blown SRH extension headers. And if you don't, you can now do micro SID, which is actually a compressed SID entries into the IPv6 header, again going to only an IP and IP if you don't need tags and TLVs. So you're able to compress a lot of segments into a single IPv6 128-bit address field, and you can actually go and carry a lot of traffic engineering paths. This was SRv6, to understand the concept of where I'm going to go afterwards. Now I'm going to talk about COIN, which is something new in academia, starting to be done into ITF, which is how you start to do computing in networks. As we go along, as the processors get more agile, as we can start doing more programming into the ASICs and the capabilities you have in FPGAs that we're pushing out the fields, we're now going to the level where why do we need to jump everything back into x86? We can now start to reapply programming and use those equipment in the network to be able to do some functionality if you want to do it at a different model versus doing it into a standard server farm we would normally do when we started the NAV transformation. This is something which is happening at ACM SIGCOMM, and there's a research group in ITF about this. For us, what it means is we started transformation, and right now the model was, well, let's try and transform all our 75 years old and even older COs into a big compute farms, change the cooling, the power, all those things, try and find a way to have cost per bit efficiency, try and find a way to have our VNFs that are not gonna burn out too much CPU cores, and you think about doing virtualization and cloudification, and what you're actually doing is a big server with 2 VMs. And the number of that ratio of complexity and the cost associated to it was not really something that helped out overall. I think everybody got challenged with this. At the same time, we didn't really solve the OPEX challenge because changing a model of operational to go out and to do all those things really changed something in the really complexity in how we operated on our network. When you start to think about things like COIN and segment routing v6, you can start to think about service programs which rely on the hardware when they can. They rely on software when they can, but you still want them to be able to use the cloud native principles, the way we now know how to build software, how can we apply that everywhere to every processor we have in the network? For us, it sometimes improve throughput and latency. Will also improve cost and efficiency sometimes for the pure throughput processing. Improves in energy efficiency. Hardware-assisted offload, our colleagues from Ericsson explained it before. We now see a democratization of our ASIC programming. We now see academia, languages more open for people to be able to program and experiment with those kind of technologies and those hardware. And we now see also a need to have a tighter coupling between cloud and metal. And I gave examples of what we can now do with programmable, like in-network computing with SRv6. You can start to create network functions, basic network functions. You don't need a big VM and big license software to be able to do just pure policy ID or rate limiting policy on an ASIC, which is really done, may be able to do this. So what is service programming? Is to be able to use all those services, all those programming notions of the network, plus assign that or link that to an IPv6 address to make it reachable and easily distributable, so that you can create service programs within your network, your service mesh across your network, and make it simpler to actually operate compared to try to retrofit every building you have in your company to be able to do a full cloud. It doesn't solve everything, but it helps in some variations. And just there is a few examples of some behaviors that you see in SRv6, like cross-connect equivalent to pseudo-wire or layer 3 lookup in both v6 and v4. So what is service programming? Is an extension of network programming which support traffic engineering and all those mechanisms, but for the notion of service chaining or service creation. Right now, there is a data plane. I just talked about this with SRv6 that is able to be spread across multiple targets, not just software. Although we did a lot of efforts with VPP. I'm going to talk about it later. Right now, the current control plane to create that service discovery is more oriented towards IETF standards. It's BGP, extensions to BGP, BGP-LS. Well, I don't see any VNF vendor really rushing to go and code BGP-LS in their software stack. So my thought was, isn't there a way where we could have more cloud-like, SDN-like control to this to be able to create those kind of service discovery? And this is where Ed came to me a few years ago and talked to me about NSM, and that the ticker clicked. And this is where I got to that level. Or if I can use the notion of service programming, but be able to leverage cloud principles like NSM, where could we go? So now I'm going to talk a bit more about the ongoing work we have right now with NSM and SRv6. I wish I could code like Nikolai. I cannot, so I do other complex stuff. So first, we started with basic support of SRv6 in Contiv VPP. We don't do NSM yet. We did the first idea was to be able to do CRD-based chains, but it also helped us learn how to actually try and figure out how to SRv6 can work in Kubernetes and try what are the workarounds you need to do with SRv6 and Kubernetes to make it work. So it's in Contiv, it's actually public, it's open source. There's a bunch of implementations of how you can actually do pod-to-pod communications, basic service chains, and even service creations using SRv6. Both v4 and v6 overlay. Now we're working on a bit more on the PNF integration, which is something we still have in our network, and how can we actually integrate PNF integration? So the trials we've did is, in a next-gen CO, could we leverage something like a programmable hardware to create some kind of a pipeline-bound chains of our physical hardware and make it visible through NSM, so that our service mesh of our clusters could actually see it in its registry as an actually existing environment. My initial thought was, don't try to make it a Kubernetes node. I realized it's actually simpler to have a hardware platform, for example, open platform with Tofino, be part of a Kubernetes cluster, then not be part of a Kubernetes cluster and try to make it part of NSM. So actually running Kubernetes on the box, enabling NSM manager was actually simpler. And actually it made my cloud now more oriented towards hardware, I was quite happy. So, and I wanted to avoid going down the ODL and ONOS path because I did both. And I wanted to go more in a cloud-oriented manner and leverage APIs instead. again, Bruce stole my thunder this morning. So, the purpose was how can I extend NSM, SRv6 to physical devices, even those that cannot support it. So in our case, the Tofino box is able to do a proxy function for physical devices. And what I actually see is a SID of a pipeline in hardware where physical functions chain together, but from the overall network, it's seen as a single SID. It's really only like if I were doing the CNF testbed in a pipeline mode, and that would be the same, just that it's done through P4 hardware. On the other side, I have what's coming from the ingress of our access network, and this is where there's a bit more work to do with the ingress gateway. How can I make a physical device be an ingress gateway for an NSM cluster? That's the next step I'm going to have to figure out in some ways. But that's been some ongoing work, and actually been successful at this. On the second one was, how can we start integrating PCE? Our transport network runs segment routing MPLS right now, but it will at some point do something else. But our traffic engineering principles will be relying on SR and PCE. I don't want to run PCE into my Kubernetes cluster. So how can we integrate NSM clusters into that domain so that in between those two clusters, I could have a standard transport mechanism so that actually it bridges the gaps. And how can I inject my SID list through those servers to the traffic engineering path so that when my NSCs go and talk to some external devices, they can leverage a full traffic engineering path if I need to have it. The second, the other one I'm going to have to try and figure out is the local and remote chains in UCPE. As I explained, this is something I'd like to figure out a way, whether it's an extended version of, like I did for the physical devices, having a UCPE device that you push to a customer be part of a Kubernetes cluster, which I personally don't like, but we've tried the labs and it works pretty well. I like to have the other way around, and could the NSM manager, in that case, work more like in a virtual kubelet mode, like disconnected from a Kubernetes, but still be part of the NSM registry and domain, so that I can still inject local mechanism, and if I need to scale out to cloud, I just use a remote mechanism, rather than, let's try and to do SROV and VLAN plumbing internally, but then afterwards try and find a way to do an SD-WAN across multiple clouds. Can I leverage that same kind of elastic model of a service mesh through NSM in different ways? So, in conclusion, what can NSM bring? Well, it provides already a cloud-ready control plane for inter- and intra-domain clusters. Today was actually a good view that it does. It can interface with physical NSCs, orthogonal to SDN flavors. The reason, right now, I did NSM Manager instead of a ENSM. The purpose was, can I try to do, for example, the physical devices like I did, or an SDN gateway? Normally, right now, industry-wide, if you have an SDN gateway to terminate with a SDN CNI, it's kind of all interconnected. There's a hardware compatibility metric and software metrics that if I want to do gateway with Contrail, I need those boxes. If I want to do gateway for something else, Nuage, I need those boxes. I would like it to be independent. I would like to be able to say, I have those boxes, these are gateways, this is where my physical network will come in. Then can I just switch to virtual in that case with an NSM? That would be something interesting. I can now inject additional intelligence through PNSMs. Again, Bruce stole my thunder. I can potentially reconcile the local and remote dilemma of the UCPE if we push a bit further. Also, it provides an innovative network service registry architecture independent of SDO standards and going to the BGP ratification or list control plane, list mapping servers, and all those things. So I think I rushed that into about 8 minutes, but no, 20 minutes, that's not good. So any questions? Yes?
So SRv6 is great, but why PGP did not accept it?
It's a big, we're going to need a few beers for that. Actually, there's a model of you being able to use SRv6 without having to change the GTP tunnel mechanism. The enhanced mode was the one that was going to CT4 to extend that. That did not pass. I can still deploy SRv6 and not remove GTP. You lose some capabilities, but it's still workable. I think it's going down that mode at 3GPP, it's a big, I think it was a big transformation. And I'm not sure at that time at the CT4 everybody was willing to play to that. At the same time, at the time it was proposed compared to the dates for the releases that were coming. The main driver is SRv6 is a great data plane. It's IPv6 based, so I can route everything. But we're source-based routing, so you don't want to have to play every time with the source packets and figure out like every time there's a change in the network, I'd go and change the source entries. Through NSM, I can actually create a mechanism where the services are discovered, which is right now no one discovers. Right now, it's a kind of always orchestrated. This way I can have more dynamicity in how my network behaves without having to every time go and change the packet headers at the source. Plus I can live around failures easier. I can do any casts with IPv6.
So how far are you with the implementation of this?
The one where I'm most advanced is the P4 switch, because we have clear use cases of trying to find a way to switch. We go MVP mode, so what can we solve first, which actually not just a lab experiment, but physical devices. So that's the first one. The UCPE, we did trials. It's like a good proof of concept. We would never go and push Kubernetes at every UCPE device, although people proposed it. I would never go there. So it was just a proof. The trick is, how can we do something different? I think the next step would be, can we push differently the model where we can leverage the same NSM, but in disconnected mode, I would say. So those are the two. But now that I saw Bruce's demo this morning, my PCE is... Other questions? Thank you very much.